Um, my name is Dr. George Flanagan, and I work here at Oak Ridge National Laboratory. Right now I'm working with the International Atomic Energy Commission, and we are doing some training for that organization with respect to the Design Information Questionnaire and Design Information Verification process for research reactors. So this lecture will be a spin-off of this work we're doing for the IAEA to familiarize their inspectors as to what is going on in the process of doing a Design Information Questionnaire and what's contained in that, and also for Design Information Verification process. So what is a Design Information Questionnaire? And what is it used for, and what is contained in such a document? And in the second part of the lecture, we'll talk about what is a Design Information Verification, what it is used for, and how it is carried out at a site. Design Information Questionnaire is really a document that's prepared by the facility owner and sent through the member state to the International Atomic Energy Agency by treaty agreement. The purpose is to provide the information to the IAEA regarding the design and the operation of a facility that a member state has declared is as being available for inspection by the International Atomic Energy Agency inspecting organizations. In the United States, this would be declared facilities would include those which are licensed by the Nuclear Regulatory Commission. That would be those research reactors that are existing in the U.S. which have an NRC license, or the power reactors in the U.S., or fabrication plants in the U.S. It also includes some DOE facilities, includes the high-flux isotope reactor, for instance, at Oak Ridge National Laboratory, and also includes the receiving basin for off-site fuels, the so-called rub-off facility at the Savannah River site. Otherwise, if it is defense-related facilities, they generally do not, in a weapons state, they do not receive IAEA inspection permission. What kind of facilities then do have DIQs? They exist for research and power reactors throughout the world, and that includes critical facilities as well. There are also DIQs for reprocessing plants and fuel fabrication plants, for enrichment plants, and for general storage and research facilities such might have a hot cell where you would handle radioactive material or possible fuel materials. Each DIQ at each one of these facilities then requires a different set of information from the owner or the operator regarding how they operate and design such a facility. The majority of this lecture will be focused on those related to reactors and power reactors. So for a reactor, there's a lot of detailed information required that has to be supplied to the agency. Includes the general areas of interest, starting out with the location and the ownership. Who are the owners of the facility? Who actually is responsible for the operation of the facility, which may be different. As an example, in the Department of Energy, the owner is the Department of Energy. The operator of the facility is one of the contract organizations, such in the case of Oak Ridge National Laboratory, that would be the UT Battelle organization. The general reactor description information is provided first. That would be a facility description, the layout of the facility, other buildings associated with the facility other than the reactor, such as associated hot cells, spent fuels locations, office buildings, and research facilities that might be related around a research reactor. In the case of power reactors, it also includes information as to the number of units on the site, what are the power levels that these reactors generally run at, either both research and power systems. What is the reactor type? Is it a pressurized water reactor in the case of a power reactor, or a boiling water reactor? Or in the case of research reactors, there are a wide variety of types, and more descriptive information then would be required for those because they are probably not a standardized design except for the trigas. The other area is the type of refueling operations that go on this reactor, including the refueling frequencies, the number of fuel materials that are moved during the refueling operation, and any excess issues related to personnel during the refueling process. Other general information might include the enrichment of the uranium being used for research reactors. This can range from natural uranium all the way up to 93% enriched uranium-235. And if you have any plutonium in the fuel elements, such as mixed oxide fuel might occur in a power reactor, the concentration of that plutonium in the fuel assemblies would be required. If they are thermal reactors, they would have information as to the type of moderator that the reactor uses. This might be graphite, heavy water, light water, or beryllium. The type of coolant used in the reactor, of course, in power reactors, this would probably be limited to light water reactors or gas cooling systems or liquid metal. But in research reactors, you may have other kinds of coolants as well, and they would want to know the properties of those coolants, the amount of coolant you have on site, and the location of the coolant storage locations. Also, if the reactor has a blanket, such as a breeder reactor might have a blanket, then you would want to know what the blanket composition is, how many assemblies you have, and if it has a reflector, what kind of reflector. Are you using a beryllium reflector? Are you using light water or heavy water? And this kinds of information will be required on the questionnaire in some detail. After you get the general reactor description, the next issues on the design information that the IAEA would like to have are the information related to the nuclear material itself. For instance, what are the types of fresh fuel that you have? Is it in the form of a metal fuel, an oxide fuel, or perhaps a trisol graphite type material? What is the enrichment of the fuel? Is it natural uranium? And of course, in research reactors, as I mentioned earlier, it can range up to 93% enriched. How much fuel do you have in a reactor core? What is the physical and chemical form of the fuel? In most cases, the fuel will be in pins or plates, but in some research reactors, it may be actually a liquid fuel. It could be in the form of spheres, such as in gas reactors. So they do need to know the type and physical form of the fuel. A description of the reactor assemblies, should the reactor actually have assemblies. There are some reactors which do not have assemblies or do not have heterogeneous assemblies. But for those that do, they would like to know, are these square assemblies? Are they hexagonal? How many of them are there? And what's inside the assembly? Are there pins inside the assembly? Are there fuel plates inside the assembly? Because this is important when we get to the accountability area. What does the fresh fuel look like? That is, what is the geometric form? That is, inside the subassembly, you may have a fuel pin. So what's inside the fuel pin? Is it an oxide pellet? Is it a slug? What are the tolerances on the fuel loading that the owner gets when he receives the fuel from the manufacturing agent? This would be including the physical tolerances on enrichment as well as the dimensional tolerances on the fuel. And what is the cladding made out of? Is it stainless steel? Is it zircaloy aluminum? What kind of cladding does the fuel have? And what is the composition? And is it the fuel bonded to the cladding? What is the bonding material that one uses? In the case of liquid metal reactors, for instance, some of these have sodium bonding between the fuel itself and the cladding. Can you move the material within a subassembly? That is, can pins be removed from the subassembly, or is the subassembly essentially your basic unit? This, again, is important when it comes to accountability and control. From that information, you will determine what is your basic accounting unit for the IEA. How do you identify this accounting unit? In this case, if it would be a fuel assembly, as an example, it may have a number or some sort of an etched material on the fuel assembly somewhere where you can identify this specifically and follow it through the fuel cycle process. In other cases, that may be more difficult if the fuel is not in an assembly basis and presents some difficulty for the IEA. Are there other materials in addition to the fuel present in the reactor? As an example, if you have a blanket material, you may have natural uranium, you may have depleted uranium, or you may have other material that are non-fissiles, which are still of concern to the IEA, for instance, neptunium. Do you have plutonium-238? There's a number of other nuclear materials which are not in the fuel cycle, but which are of concern to the agency. The next thing they will ask you about is how does the material move through the reactor process? They would like to have some flow sheets which show on these flow sheets the accountability points. That is, where are you accounting for the fuel in terms of its makeup, its chemistry, its isotopic composition, And how are you looking at the inventory? Where are your inventory locations? You may have material in the core, you may have material in transit, you may have material in storage. So they need to know where these various locations are in your facility from your earlier facility layout so that they can track these and monitor them. In the inventory area, they would like to know how much fresh fuel is on hand generally at the site, how many fuel elements are in the core, how many are exchanged in the core during the refueling process, and how many are located in the spent fuel pool. As an example, there may be fuel for research reactors in other locations. You may have fuel in a hot cell that you use for examination purposes. You may have fuel in a chemistry laboratory where you're dissolving the fuel looking for particular issues. So they would also like to know that as well. What is the load factor that the facility generally runs at? This gives them, this is related, of course, to the burnup of the fuel, how much plutonium can be produced in the reactor over a given period of time. So they would like to know what your average load factor is. Also, the core loading, that is the fuel loaded in multiple, in batch form, that is the entire core is replaced at one time, are individual fuel elements replaced at one time, or do you place, say, a third of the core at one time and allow the core to remain in the reactor for longer periods than one refueling cycle? And if you do that, do you actually rebalance the fuel? That is, do you take fuel out of one location and put it into another location so as to even out the burnup on the fuel? This is all related to the refueling process and the core loading process. Again, this goes back to how do they can track the inventory of the reactor material that's in the reactor, that's in the process. What is the burnup that's generally used on the fuel? For research reactors, this could be very low, or in some research reactors, this can be extremely high. As an example, in the high flux isotope reactor, the burnup is as high as 30 atom percent. That is 30% of the uranium-235 is used in one fuel cycle. But on a trigger reactor, you may have almost negligible burnup because the reactor operates at such low power levels. In power plants, nuclear power plants, the burnup, of course, is related also to the amount of plutonium that's produced in the fuel in a light water reactor. What do you do with the irradiated fuel? Do you reprocess it? Is some of it processed? For instance, you may do some, for a research reactor area or a test reactor, you may take some of the fuel out of the core and process it, and other fuel is left in storage. And if it is left in storage, is the storage wet storage? Is it dry storage? Is it on-site storage, or is it at some sort of a national storage facility? Then we go down to how do you handle the individual pieces of material? If the spent fuel or the fresh fuel comes in, how is it packaged? Is it brought in as an element in a box? Is it brought in some sort of a carrier or licensed transport device? How is it stored? Where is it stored? And what is the accessibility to that facility in which the fresh fuel is stored? What's the maximum capacity license for this facility for this fresh fuel storage location? Can you put more than and who monitors this? Is it the licensee that determines this, or is it part of the facility license? Or is it just simply the space that's available? What kind of fuel prep is done on the fuel once it comes into the facility? Are there any quality assurance aspects in which the fuel is examined? If so, what are they? Do you take an assay of the fuel to confirm that the enrichment, the isotopic composition, material composition of the fuel is as it was when it left the fabrication facility and was essentially contracted for? Or do you accept the results from the fuel fabricator? If you do that, where do you do it, and who does it? The other issue is how do you transfer the material from one location in the plant to the other? As an example, the fuel may be trucked to the facility or brought in on a rail car. It's then brought probably into some temporary storage location. From there on the site, it may be transported in smaller quantities to another location on the site for prep and assay, or it may be kept all together in one location. And do you need cranes to transport the fuel? Do you need forklifts? What kind of special equipment do you need for picking the fuel up? All this is in the fuel transfer process, and it's important to know this to see what the ease of material movement might be should someone desire to take the fuel. What is the route followed by the fuel? Obviously, as I said, it comes into the facility either by truck or rail. It's unloaded. It's put in some sort of a building of some place. Is the building within the reactor building? Is it a separate building? And if so, then follow the fuel through the process from how it gets from the entry site to the site, actually to the core, and then when it's exiting the core as a radiated fuel, where do you take it, and where does it finally end up? When you get to the reactor vessel, then one needs to know how is the fuel actually put in the reactor vessel. Different reactor types have different fuel loading schemes. There are even pebble bed reactor concepts in which the fuel is continuously brought into the reactor and taken out while the reactor is running. That is also true of the can-do type reactors. So what equipment is used for doing this process? Do you open the vessel in order to do this process? And if you do, what special fuel handling equipment is used to either locate the fuel that you're going to remove and replace, or to remove the fuel if it's in operation at the time, such as a can-do. What is the core design diagram? How is the fuel laid out in the core? Who keeps track of the core design diagram? And when you move core material around inside the core without actually removing it from the vessel, how is this kept track of? And how do we assure that it's actually in the right location? In some cases, this may be done excuse me, through monitoring equipment. It may be done through simple visualization. But they would like to know how this material is tracked even when it's inside the reactor vessel. And then the number and size of channels for the fuel and control elements. In some research reactors, as an example, the fuel control assemblies may be actually one assembly. The control actually may be a part of the fuel assembly. It also may be a case where the fuel is actually removed as part of the control process rather than using an absorber, as an example. They would like to know these unique features that might differ from, say, a power reactor, where for typical power reactors, this kind of information is well known. What is the flux level in the reactor? This is critical to the IAEA's information base as to whether or not the flux is high enough in order to produce significant quantities of fissile materials such as plutonium-239. What is the thermal flux and what is the fast flux in the facility? What kind of nuclear instrumentation is present in the facility? How many neutron monitors are there? Where are they located? What is their range in terms of flux level that they can be used for? And what kind of gamma facility monitoring do you have? And what kind of air monitoring equipment do you have as well in case there's leakage or movement of material in the inner environment? Further on material handling, what do you do then with the irradiated fuel? What is the layout of the fuel pool, if there is such a thing? How about your dry cask storage? If you're in a power reactor facility, many of them have those today. Also, some facilities that have multiple units have on-site fuel storage for each unit, and then they have a common fuel storage location where when the fuel cools, they move it to a central location in preparation perhaps of shipping it off-site. What is the method of storage? Is it a dry storage environment? Do you store it in water? Or do you have other storage capabilities that are unique to your particular fuel type? What's the maximum capacity of your fuel storage capability, irradiated fuel? How do you cool that facility if cooling is needed? Is it a pool, an example, and therefore you have pool cooling? Is it air-cooled? It may be, in liquid metal reactors actually may be liquid metal cooled. And then when you move the irradiated fuel, what kind of casks do you use? Since these would more likely be shielded, and how large of a crane or handling machine do you have in order to pick this cask up? And what kind of layout do you have as far as floor loadings for these kinds of casks? Can they be put in different buildings than were intended, or would they exceed floor loadings? And what's the activity level on the surface of either the fuel element itself or 1 meter from the fuel element? And also the same for the cask. What is the a dose on the cask and 1 meter from the cask. This is also important for the purposes, can this cask, if it is transported off-site, can it be tracked, and do you know that there's a radiation dose and therefore would be considered a special handling process. And again, back to the fuel handling equipment. When you're moving it off-site, again, you have to determine, does this come off by rail, by truck, barge? What other methods do you have to move these fuel casks? Now, in case of research reactors, you may have some material testing going on in the reactor that is not part of the fuel, but it may be testing other kinds of fuel in the reactor. So if you have material testing going on in your particular research reactor, what is tested? That is, can you test fissile material or fertile material? Are you limited to, say, isotope production for medical purposes? And how do you do this, and why do you do it? What is the purpose of the test that you're conducting? What equipment is needed in the site? This might include hot cells, glove boxes. Do you declad material in this? And if you do you create waste? And if so, where does the waste go? What about special shipping containers for these material test assemblies? And that includes, as I indicated, both the scrap and the waste material as well. Because you can also, in some cases of reactor fuel types, when you are dissolving the fuel element, for instance, the waste stream will contain fissile material because you can't get 100% separation. If you are storing material and irradiated materials, again, in a research reactor environment, are they stored in this particular building, or are they brought in from somewhere else, and how many are in the building where the process is taking place for material testing, and how many are left outside the building? And then what is the layout of the facility? Where does the fuel come in? Where does it go through, say, the hot cell or the glove box or the chemical dissolution facility or whatever you're doing? And where does it leave? And where do the waste streams leave? And then if it needs to be cooled while it's in this material test device, such as in a hot cell, how is that provided? And where does the stream of coolant come from, and where does it leave from the facility? So these are all the kinds of details you have to include in, if you have a material test capability at the site. The other areas that they're interested in are the physical and safety measures that are taken to protect the material you have in transit or on site. That is the physical protection. Do you use gates, guns, guards, or any other devices that they would need to be aware of in terms of physically protecting the fuel? And what are the safety and health rules if you were an inspector, as far as that you have to comply with if you were to be on site? This might include badging, dosimetry, training, and other aspects of being having a site inspector. And then as far as material accountability and control, the MC&A aspects of what you need to provide, you need to indicate how are receipts handled. That is, what is the paperwork process? How is this recorded? Who does the recording? Who has to sign off on the recording? And where are these receipts kept? Are they computerized? Are they kept in paper form? And are they locked or not locked in people's offices or in vaults? Who keeps track of the shipments? Who arranges the shipments? That is, if their shipment is fresh fuel, let's say it's a highly enriched uranium coming to a research reactor, how is this shipment arranged for? How is it protected? How is it received? And who transfers the authority for the fuel from one organization to another? And then the physical inventory itself. What are the methods used to determine either the basic unit accountability, or in some cases the isotopic quantities of material that are brought in? How accurate are these methods and instruments you use? How is access to these? Can other people access this information? This would be a concern about, say, recalibrating the instrument. And who does so, and how is that recorded, so that we know that the instrument has not been tampered with, or in other ways somehow variability has been introduced into the material accounting process. How is all this verified? Do you use sampling of known material as a verification process? Is it done by the owner of the facility? Is it done by a special outside organization that does this as a process or provides the services? and how often is it done? What are your limits on nuclear loss and production estimates? How accurate do you need to be, or how accurate does your license require you to be in determining the material that you either are bring into the plant or that you're producing in the plant while it's running? And how are all these records kept, and how long are they kept, and in what form are they kept? This is all important to the inspectors when they come to your facility to look at this information. Also, we talk about the features of containment and surveillance methods that are used. At each measurement point, for instance, you describe the process by which the fuel is actually measured. What are the anticipated inventory changes that one would anticipate you would see in such a facility? In other words, is there variability in your fuel type? Are you doing research so that you may see a wide diversity of materials that are being measured, from, say, test assemblies all the way to real fuel assemblies? And what are the physical and chemical forms that you're using to do your measurements of material inventory? These might you do, in other words, do you have to dissolve the material and use a chemical process, or can you do it in a physical system and use counters? In liquid fuel reactors, for instance, there is no physical inventory itself. It would be obviously in a liquid form, but in some cases it may have to be in a very high temperature form. That would certainly complicate measurement processes. What kind of containers then are needed to doing these measurements? Are they done in small quantities and therefore unshielded? Are they larger processes? If you don't do it at your facility and you contract this process, is this material packaged and sent to another site, or do they bring their facilities to your site? And what are the procedures, the exact procedures, so that one can say that the accountability process has been validated and can be confirmed? Who signs off on these procedures, and how much training is required in order to maintain the sampling process? What measurement methods do you use? Do you use three-dimensional processes for doing counting? Do you do chemical extraction? So what are the accuracies of these processes? In some, by far, the process is much more accurate than in others. What is the calibration schedule for the equipment you're using to determine this accuracy? What if you're converting, that is, some sampling, or what we call source data, sampling information, and converting that to batch information? How many samples do you take to determine this is the batch representation? That process is statistical in some sense, but it needs to be outlined. It should be part of the procedures. How many batches do you look at per year in your measurement and sampling process? Do you only take one batch and then take samples from that batch, or are you doing multiple batches and take samples from multiple batches? And what are the items that are actually used to form up the batch? Is it fuel elements themselves, multiple fuel elements, or is it the fuel pin level, or even in case of fabrication plants, it may be in the process of the oxide fuel pellet. So the information then would be also what material is in that batch. Is it uranium, uranium plus clad, uranium plus plutonium in the case of mixed oxide? In case if it were to be processed material, what is the composition of the ratios between the uranium, the plutonium, and the clad material? And who has access to this material while it's being measured? Is this limited access, training required? Who are the supervisory people that assure that this access control is maintained? And who also has access not only to the material, but who has access, as I already mentioned, to the equipment? Who does the calibration, and how are they qualified to do the calibration, and how do you know that this calibration was done properly? Who oversees this process? And then what are special features that might be related to containment and surveillance measures that are unique to that particular facility? In some cases, for processing plants, these are unique to the facility because the process may change. You may use multiple processes to do different stages through the plant. and each of those has to be different surveillance and methodology used for materials accountability. Sometimes the information that we ask for that I just mentioned, which is a long, detailed list, is not available or not even provided. One reason might be that it's classified. Another reason, it might be export controlled. That is, that particular process may be unique to a particular country who does not want to share this information to inspectors from other countries. And therefore, through the IE, which is more of an open process, this would be a violation of their export control policy. Some of it may be sensitive. That is, it may be a private company's process in which they do not wish to determine such things as, let's say, the calibration sensitivity, the accuracy of this methodology, and therefore they don't share this with an organization which has multiple member states. Or in many cases, all this detail that I just talked about may just strictly be unavailable. That is, a facility has not got to that level. A small research reactor, for instance, may not have nearly this much information that's required on this form, and indicates that it's such a simple process that most of these steps can be essentially summarized into one general statement that the reactor is never refueled after it starts, as an example. Some research reactors have been running as long as 20 years or more and never had a refueling process. Don't even have fresh fuel on site, don't have any spent fuel on site, everything's in the core. So this may be one reason why you wouldn't answer all the questions. Or it may not fit your type of reactor. I mentioned earlier that there are three types of reactors which have unique fuel forms which are not standard. One might be the molten salt reactor, in which the fuel is dissolved in a salt at very high temperatures. Another is the gas-cooled reactor. Most gas-cooled reactors today use a trisol fuel. This is a very small spherical fuel element or fuel form, which does not lend itself to individual accountability because there's thousands to millions of these spherical forms to make up an entire reactor core. Another would be an aqueous homogeneous reactor, which might be used for isotope production, in which the fuel is dissolved, in this case, in an acidic solution. Again, it has no physical form, and so everything is done by a chemical process. Now, usually when this happens and the agency reviews your DIQ, they will have questions as to why certain sections are not filled out. If you can provide those up front, that's going to save a lot of time, but if you can't, they will come back and ask you the questions of, were you missing this information? How do you do the process in such a way that it may not fit into the form question, but maybe we can work up a process that describes enough so the inspectors can come and review your process if it's totally unique and not fits a standard form process. So they will work with the owner and or the member state to get as much information as possible if it has not already been provided. Or they may choose, for the cases of classified, export controlled, or sensitized information, that they will desensitize. They will put it in a form which is not specific enough to cause concern of holding this information in reserve. An example, we know we can declassify certain information, so if you can go through that process, get the general information out, but not release anything that's classified, they will attempt to try to suggest you do that. Now, what is the design information verification process, which is different than the DIQ? The DIQ is technically a piece of paper, a long piece of paper with about 60 questions, which you fill out a great deal, and then you provide not only the information that's asked, but you also provide many appendices that give you drawings and other declarative information that will help the reviewer understand more about the facility than just answering the question with a verbal or text sense. Any pictures and diagrams would also be included in the DIQ. Now, the DIV process is a process by which the agency determines whether the DIQ that the member state has submitted on a particular facility is adequate, first of all, and secondly, they verify what's on the information that is provided. First process is essentially that you bring the DIQ to an evaluation team within the agency who reviews this process and starts looking at questions, much as a safety organization would review a safety submittal and ask questions about whether they understand everything. Once that is done and that goes in the file, then for the DIV process, there are a number of stages within the reactor operational program which a design information verification takes place. If it's a new facility, the design information verification will take place, first of all, during the construction phase. They will actually go into the facility and they will take the DIQ, which is essentially what's going to be supposedly planned for that site, and they will verify that indeed the site layout and the things they can see during the construction process seem to conform with what has been declared by the state as what the final facility will actually look like. What they're looking for in this process is that there are no areas in the plant which have not been identified on the DIQ, which would be rooms or facilities or areas in the plant which may be underground, which are not shown on the original diagrams, which could be used for diversion in particular. That would be what the concern might be. So essentially, are you building it according to your plan, and are you deviating from that, and if so, why are you deviating? So then this is done is to verify this information that's in the DIQ. It's also used to amplify this information. Let's say the facility owner decided he did not declare an adjacent facility, and then during the DIV process, the inspectors say, well, what's in that facility over there? Well, that's where we handle whatever it is. Well, shouldn't that be, if that's fuel, wouldn't you want to declare that? So it would be additional information that maybe was not thought about as part of the facility, in which but because it is in a process by which the fuel is transferred through the facility or material is transferred through the facility, that the IAEA would like to see what goes on in that facility in addition, say, to the reactor building itself. So they may amplify on their own site to suggest that the DIQ will also include these adjacent facilities, as an example. The other purpose of the DIV is to determine if the follow-up visits are going to be required. Certainly during the construction phase, after the construction is completed, they'll be doing another DIV to confirm that the actual plant does indeed look like the DIQ before it actually starts up. And then during operation, they may come periodically to check as to whether deviations in design have taken place in the plant itself. Has the plant been modified significantly so that either its purpose has changed, its power level has changed, the amount of material in the facility has changed? And they will periodically do inspections or verifications to determine that this process has been adequately declared and that they're not working from essentially an out-of-date DIQ. They also determine during the DIV process whether this facility is of such importance that they need to do internal monitoring. That is, IAEA may set up its own monitoring process. It may seal equipment in terms of transit containers, as an example, where seals are placed on it so that there's indications that material is indeed located where it's supposed to be and has not been tampered with. It will also determine not only whether that kind of process is needed, but where it is done. If they need to do visual examinations, they will determine where their best locations for, say, cameras might be. This all has to be worked out with the owner, however, because one cannot technically violate some of the owner's restrictions, and so you have to essentially comply with some of the owner specifics that they may not wish to have something photographed because perhaps there is a security process going on at periodic times during that in that location, and if so, this would not be something they would want to share with outside observers. So there may be restrictions on where you can place equipment. So the IAEA will generally make suggestions and then pass it by the owner, and if non-intrusive, they will probably comply with that. If not, they will come up with alternate plans. Generally, the process goes as follows. After the evaluation and the DIQ have iterated between the owner and the agency to the point where they feel that they now have an adequate set of information, a team of IAEA inspectors is assembled. In many cases, and most always, this does not include inspectors from the country in which is being inspected. The DIQ then is reviewed by each of the inspectors. They may split up the task because there's a lot of information. Many of them may be specialists in certain areas. For instance, you may have somebody who has an I&C background. He's going to be interested in the calibration processes, the measurement techniques, some of the instrumentation that's being used, how this instrumentation is maintained, etc. Another person may be a reactor physics. Another person may be thermal hydraulics. So you may split the DIQ into pieces and those expert members of the team will look at those pieces in specific. And then that a team lead is chosen who will actually interact with the facility people and essentially make sure that the inspection goes well or the verification goes well, and sets up the contact processes. First, you contact the member states to let them know that a DIV is about to occur, and then they in turn will contact the site in which the DIV is intended to take place. And one of the things they would want to check with is what's going on during the expected date that the inspectors will be there. They will try to work around, say, holidays, which may be unique to a particular country, where various people would not be available because they're on holiday. Some facilities even shut down in summertime in Europe, for instance, for a week or so, and everybody goes away except for security people, so there wouldn't be anybody to talk to. Nobody would let them in. Also, during refueling outages or places where there are special activities going on where the presence of an IE inspector will either, one, be involved where security issues are an issue, and therefore you would not want people from another country observing the process, or you may just simply say that we're too busy, we have too many people working on a refueling outage, we're trying to get this done in X number of days, and therefore we don't have time to stop everything and work with the inspectors. And generally this will be worked out between the agency and the member state. Any special training requirements are identified up front. That is, will the inspectors need to have special radiation protection training, or is the radiation protection training they may have from another facility adequate for your facility? What about site security training? Do they need special issues with respect to site security that your site would provide that the inspectors would normally not have? Special issues, are there classified activities taking place? In case of some research reactors, there may be some classified work that may take place nearby or in the vicinity of that particular reactor. In those cases, that would need to be known up front so that the inspectors can be routed away from that, and will understand why they need to be routed away from that area. Will they need escorts, and how many escorts, and where would the team be located with respect to the facility? Are they going to be on site all day long? If so, are they have escorts all day long? Will the IEA people have translators? The IEA is generally conducted its business in English, but if the facility is not conducting its business in English, then you may need translators so that the IEA can communicate with the staff people who may not be speaking English in area areas. Arrangement for passes and visas are made by the agency long before the team arrives. Can you bring special equipment on site? Many organizations now, because of terrorism issues, do not allow cameras. They may not allow handheld devices. Laptops may not be allowed in the facility. If so, they may have to be essentially cyber secured. There are a number of issues that have to take place before a team can arrive to make sure that no violations of existing procedures and processes take place, and would be an embarrassment both to the member state, the facility owner, and or the agency. And a couple DIVs, I can tell you there's been a couple cases of security violations that have been brought up and had to be handled on site. We prefer not to have those kinds of things happen. What about the team bringing their own equipment? In many cases, the team would like to, for instance, bring GPS equipment to make sure that the locations and sizes of the buildings are as declared on the facility. They may bring some sort of measurement techniques that they've devised that are quick for the team to handle, but may not be allowed on the site. And so those have to be worked out as well. If they're going to leave equipment on the site, if they're going to bring something in, install it, and run it for a while and do monitoring and then leave the site, that needs to be worked out with the organization well ahead of time, so that the organization that runs the facility knows what are the restrictions on the operation of that particular set of equipment. Hotel and travel, of course, have to be arranged. Locations for meetings have to be arranged because the team will have to do some team meetings. It may be split up, and if so, they need to have meeting rooms for the different portions of the team. They usually arrive together, and generally what they will do is spend the first day or so with the facility management. They will essentially have access to the site, get all that arranged, and then they will have a meeting about what they intend to do during their activity. This may last a week. It can last longer than that. It may be just a few days, depending on the type of verification that's being done. Any special training that they need on site will be given at that time prior, so that they have more freedom on the site after the training. Then they will get a general overview and probably a relatively long tour of the facility at a general level. After that, the team kind of decides what they want to do next. It's not necessarily a unique process by which they go through this issue. So they may break down into groups, as I mentioned, to examine special areas that they observed during the general tour that they either had not anticipated or may have anticipated from the EIQ. And information that they see during the tour, provided them by the escorts or the tour guides, will also be used to determine what they will do next on site for the rest of the period that they're there. They usually prepare a list of additional information and supplemental information either ahead of time or during the tour process that they would request that the site provide. This may be in the form of, say, drawings, where they would say want to look at the cooling system of the plant, and they might want to have more detail than what was provided in the DIQ. They would request this either ahead of time or they may request it on site after seeing the facility and looking at it. They may be more complex than they had anticipated. Therefore, they need some drawings to try to figure out how it actually works. That request of information, because it's usually on site, may be denied or not be made available because either the drawings cannot be reproduced or for some reason that they're not available or they're restricted. That's to be expected, and usually this kind of thing needs to be worked out. Usually for the DIV teams, as much information ahead of time as to information they might require should be provided. This will shorten this interactive process considerably. When the teams then break into small groups, they will go back to the facility and indicate, we would like to visit this location of the plant again, and here's how many people are going to go on this portion of the plant, which allows then the facility operator to provide the appropriate escorts and tours, or he may suggest that maybe you don't have to go to the plant, maybe you can do this by looking at the drawings, and we'll provide some engineers who might help you understand that process. This is all usually worked out to the convenience of both the inspectors and the facility owners. Now, during the trip, measurements are almost always made of the building sizes to conform to the drawings, locations of things like the stack, and then the layout of the interior. If any on subsequent visions, this information is updated in the DIQ, and then if there are any changes in the building layouts, these are identified during the verification process, and either explanations are made or revisions to the DIQ itself are made. They may be, as I said, make GPS measurements as to the exact location of these facilities, and they may measure such things as sizes of tanks, as an example, to determine that the DIQ doesn't say this is a 50,000 gallon tank and it turns out to be 100,000 gallons. They would need to know that. At the end of each day, normally the team will meet together, particularly if they broke into different parts. The team leader will gather them back together, and they will go through what they have observed, the deviations from the DIQ that they think they have observed, and this information then generally is shared with the next morning with the plant owners, and clarification is made. Many times this is simply just a matter of interpretation, where the plant owner comes in and said, no, it really is this, and you were misled, or perhaps you misunderstood the tour guide, or the drawing is in revision and it really has changed and we didn't give you the right drawing. A lot of this is cleared up, usually on site as much as possible. At the end of the entire visit, then a debrief is held with the owners, giving them a general picture of what the team has found, what it's going to go back to the agency and discuss with the evaluation organization, and what might be the next step that the owner might expect to happen after the team leaves the site. Are they going to be getting letters back to the member state, in our case it would be the State Department, to the owner asking more questions? Have they requested information which had not been provided on the tour or the site visit because it wasn't available but has to, say, be reproduced or electronically reproduced? And when will that be sent, and what will be done with it when it gets to the agency? When they get to the agency, then the team leader and the team will eventually prepare a team report which goes on file, and it revises, updates the information that's in the DIQ based upon the visits, so that the next team that comes will have essentially not only the original DIQ, but all the subsequent reports from any visits that have been made since that time. Any information that's unique and might cause some concern or question is evaluated by a set of individuals of expertise in this particular area, and that information is either sent back to the member state or is recorded for the next visit to get further clarification. So what are the results of a DIV then? First of all, did the DIQ itself represent the design of the plant? Are revisions to the DIQ required, or just clarifications that were written in the notes by the visitors? So you can get a more formal process where it is assumed that the DIQ itself has been incorrectly assembled, and we would require you to reflect this new change or these changes in the DIQ itself, so it remains in file at the agency. Or it may be simply add notes to the DIQ from the visit, which indicates that when we were there, this is what we saw, and it seems to conform, but it wasn't quite as clear as what we thought, and here's what we found out when we were there. Decision will be made as to how many follow-on inspections are necessary and the frequency of these inspections. There may be a need in some facilities. An example of a facility that had this are on-site resident inspections. That is actually IE assigns somebody to the site on a more permanent basis. This was a current example in the Japanese reprocessing plant where an IE inspector was actually working side by side, was watching everything that was going on. That, of course, is with the consent of the member state. They make special arrangements to make take with them the next time they visit some special measuring devices that they may have lacked on the first visit. So that's recorded and kept track of, so that if they need to have a new visit soon, they can bring the right equipment this time that they may not have had last time. And then the discussion about this decision as to whether you want to install monitoring equipment. If it is to be installed, then the IE will come and work with the agency or with the owner in order to get it installed, to get it essentially secured from tampering by the owner, and how that's all, and how the data is processed, how it's transmitted. All that process is addressed when they come back to the site after the visit. And then this information is provided to the owner or in the member states so that they can clarify misconceptions. If equipment is being installed or wants to be installed, they can discuss this in more detail as to the what's going to happen to it, how is it maintained, who's going to be responsible for it. All those issues have to be agreed to between the agency and the state. It can't be imposed on the state with the agency without their consent. And the other thing that they will do is they will adhere to the fact that when the next visit might be expected and who ought to be present for that next visit, so that process, perhaps people were absent from the last visit and they needed to talk to them, so they will want to make sure they're available during the next time they come and visit. And so that's generally the kinds of things that come out of these, and they all go into the file for that facility and are available for the next team when they're ready to make their next DIV. So that ends the process, and at this point, one of the things we will be doing in the course is we'll be providing a DIQ for a facility here at Oak Ridge that will probably then be used to do a mock DIV process when they come on site. Thank you for your attention.